I'm Giuseppe Maggiore, and welcome to the second part of Massive Lecture 7, where we're going to continue talking about object orientation and polymorphism, but specifically we're going to focus on advanced patterns. We will start with a little pearl, that is how to use structs to make our applications faster. Then we will talk about static fields and methods in order to have methods and properties that are shared by your classes, and finally we will dive into interfaces and inheritance and a little bit of design patterns in order to see how to create advanced polymorphic systems on top of everything we have seen so far. Let's go. Continue our very long overview of the very rich class and polymorphism system of C#. What a huge language is it. Now, I mentioned many times that classes, like our billing counters here, are all stored in references in the heap. And, well, there is one tool which is called the garbage collector, which looks at all the references on the heap and frees the space on the heap memory, because we don't have infinite memory, so we have to be careful about it, by removing all the classes that are not referred to by any active instance. So basically the classes that are still there but no one is using anymore are garbage collected, because they don't play a role anymore. This means that every class we add puts a little bit of weight on the garbage collector. Moreover, when we deal with references, well, instances of classes can end anywhere in our program, and they can also end up in very distant locations in memory. And if we have an array of references and they are all sort of everywhere in memory, one of the results of this is that jumping around through the memory can be quite bad for our cache consistency of our, so it's the cache is one of the most important performance instruments of our CPU. In order to solve the problem of weighing too much on the garbage collector and putting things in a more predictable memory pattern, C# has a different way of defining data structures, which is called structs. And I think it's actually quite important to have seen structs at least once in life. When you have a small data structure, let's say a two-dimensional point, so for this kind of little thing you will very often see structs. Let's say that we have x and y, okay, well done, IntelliSense. Whenever we create an instance of a point 2D, so let's say P is new point 2D, and then we can add x is 0 and y is 0. The way this is going to be stored is actually pretty straightforward. We have the top stack frame, and in the stack frame we have P, and P is simply the data. And if we want to make a copy of P, let's say P1 is equal to P, then on the stack what we get is very simply a full-blown copy. And we actually should be able to show this by running this with the debugger. You remember that if point 2D had been a class, then P1 and P would be the same reference. So let's try to change, for example, this to 10, and you can see that P is completely unchanged. Whereas if we make classes out of them, then let's change P1 to 10, and you get the warp gate style change that can actually be pretty confusing. And actually y should also change here, but we don't get to see it. Yeah, but it does, because they are the same reference. So structs are these little structures that are stored in memory wherever you put them. They are copied around, hence it's a good idea never to have a struct that is bigger than a dozen fields, so you can have it for little mathematical quantities, for little counters, etc. Structs are immutable, can very easily be made immutable, and their copying mechanism is sort of a precursor of the copying mechanism of records. And yeah, they can be one of the most important instruments for making code quick. Now let's make a quick experiment about this. Let's create an array with a lot of structs, like really a lot. Let's make this parametric. So number of instances will be, say, well, what is this? 1,000,000? Yes, it's 1,000,000. Okay. So p's, this will be our point to the array with the number of instances. Okay. And then, of course, for I is 0, I smaller the number of instances. Now we initialize all of them. So we say ps of I. Oh, okay, very, very well done. Intelligence, all right. And now let's scramble them around. So I'm going to screw up the memory consistency of this. So I will say that ps, well, I pick another index. So let me create a random number generator. There we go. J is random.next. So it's a random number between 0 and let's pick the overload with the max value. And this is number of instances. Very good. And now I swap the one at I with the one at J. So now they're not in the same place. So let's call the first one point I, and this will be points of I. Let's have point J, ps of J, and then we simply reassign them. Swap so ps of I becomes pj and ps of J becomes pi. And almost done. Almost done. Now we do something with the values. So we have the sum of the values of x, and we have the sum of all the values of y, and then we go through all the instances and we say that sum x is increased by p of I dot x, and sum y is increased by p's of I dot y. Very good. And this bit we want to time. So let's create a new stopwatch. We start a new stopwatch. Oh wait, what is happening? Okay, we were missing a bit of diagnostics, no problem. And here we say, oops, stopwatch dot stop. And we print console.writeLine stopwatch dot elapsed milliseconds. Okay, so see how many milliseconds this little program took. It's 1,000,000 instances, so it shouldn't take that much. Okay, let's increase it to 10. 10 million instances. Okay, it's taking 26 milliseconds. Now, we turn this into a class. Quite an incredible difference. What is happening? And I really wanted to show, that, yeah, you change a keyword basically and your program gets, in this case, 10 times faster. What is happening? Well, when we're dealing with the structs, whenever we swap, we make a copy of the struct, meaning that as we then go through the structs in the array, one after the next, then what's happening is that with the structs, they are all sequential in memory. So you're getting from the first byte to the last byte of the array, you're reading them in order. And the CPU is super fast when doing this, because when you get a struct, actually, what gets loaded into cache are also the next ones, because very typically you will process memory in this sequential manner. But when dealing with a class, because of the swaps, not actually making a copy, we're accessing random elements in memory, basically. So we're simulating a chaotic access into memory. So first we read something at byte 10, then we read something at byte 20,000, etc. And every time the cache is empty, and so blocks of memory have to be fetched into cache for the processor, for the CPU to be able to work on them, resulting in a really dramatic difference. So when you see structs and classes, just be aware they can have a massive impact on your program, and, well, structs are not really just a little toy. They can be super important. Still, classes, when compared to structs, even though, yes, they are sometimes a bit slower, or sometimes a lot slower, like we've just seen, are more flexible. The fact that classes are reference types makes it possible to do all the same things that we did with records, inheritance, and interfaces. Let's show a very classic example of this. Let's define a class shape. And a class shape, well, let's say it has a name, why not? Publicly gettable, privately settable, as is usually the case. Then we have a constructor, takes as input the name, assigns the name, very good. And then let's say that we have a draw method. And the draw method of the shape as it is now simply prints that we are drawing the shape name, drawing shape this dot name. Very good. All right. Okay, so for now the shape doesn't really mean much, because, well, we want to be able to draw shapes to the console. We want to be able to do something of significance, but just printing a name, that's not exciting at all. So what we're going to do now is we're going to adjust the method draw and make it virtual. What does virtual mean? Virtual means that draw has an implementation, which in our case is relatively banal, it's not very interesting, but a class that inherits shape may redefine the draw method. For example, class square inherits shape, and now, well, let's generate constructor, because the error that we have right now is that the shape constructor requires a name. Square automatically gets a constructor without parameters, but that constructor is not compatible with the constructor of the shape, because if we basically say that every square is a shape, or if you want, contains a shape inside it, well, that shape needs to be constructed, and that requires a name. So the constructor that C# is suggesting us, or Visual Studio Code, I should better say, takes as input the name and calls the base constructor, which, as the highlighting is suggesting, and I can actually jump to it, is this constructor here defined on line 21. But because this is a square, it also has some extra information of its own. For example, the square has a size with, get and private set. Indeed, very good. And, well, we do need to get the size, so we will get the name and the size. A size is equal to size, very good. So you can see now that we are building the square, which has its own extra business logic, on top of the business logic of the shape, which is admittedly not that much. The most interesting addition, though, is that we can override the draw method. Override means that if we have an instance of square and we call draw, the draw method that is called is the one on line 25, not the one on line 13. Now, we start by calling base.draw. We get the little header saying drawing shape and then the name of the shape. And then we perform the actual drawing of our square. So let's see, well, we accumulated the square. It's a very simple algorithm. For I, well, this is the row, and how many rows are there? Well, of course, size, then the columns, and again, we have size columns. The square is the square followed by an asterisk, and then here the square at the end of the row gets a /n, and finally we can print console.writeLine square. Okay, now let's initialize a square. We want a name which will be square1, and the size is going to be 5, and then we can call square1 dot draw. Let's run this. Okay, now we get drawing shape square1, and of course we get the 5 by 5 square. Let's take a look at what the debugger shows us about this data structure. Okay, so square1 has type square. You can see it here, it's marked. It has a name, even though the name has not been declared on the square. It has a name because it's inheriting from the shape. Let's enter the draw method. Okay, and let's take a look at base actually. Base refers to the underlying shape. Let's see if I can evaluate base. No, it's just a keyword actually, it's not really a reference. This is a reference, base is a keyword. It's an interesting distinction. Let's enter. Even though that's only partially true, but still, now we're in this. This is of type, look, it's interesting. It's saying this shape square. What does it mean? Now this is the static type. This is the type known to the compiler, and of course inside the draw method, this reference has type shape. But the dynamic type, the actual type that it has right now in memory, that's a square. And so you can see that indeed there's a square in there. And if you look at this, well, of course there's name, and the size is not available because a shape might not have a size, because not all shapes will be squares, but it's there nonetheless. Now, let me see if this is allowed. No, it is not allowed. So base is very simply just not. It's really not a reference. Okay. Now here I'm saying that square1 is a square, but even if I were to say no, it's a shape. Well, so what's the difference? Let's go back to the square1. Square1 has a size because it's a square. But if we say no, it's a shape, then there's only name and draw. The result will be exactly the same, because calling draw calls the dynamic, the most specific implementation of the draw method. So it calls the one of the square. But even though the size is there, because of this change in type, the specific things that are available in the square cannot be used directly. They can only be used indirectly, for example, inside the draw method. Also notice that a type conversion is taking place, just like we have seen for records when using inheritance and implementing interfaces. Because we said here square1 is a shape, but we try to put a square into it, well, okay, the compiler doesn't really complain about it, because every square is also a shape. So we're not losing information, we're just forgetting about some extra things that are there, but we're not risking violating any of the constraints required by this declaration by the fact that we actually just want a shape. So saying I want to track less information and you put more, yeah, that's okay. And that is indeed the magic of doing things by references, because if you were to copy these things statically like we did for structs, yeah, then this mechanism would simply not work. So indeed, these references and the whole struct things actually has a reason to be. You need references in order to implement this well. Let's say that we also had another shape, a simple rectangle triangle, and well, the columns will go as far as the row. Well, of course, this is not a square, but rather the triangle itself. Okay. Now, okay, let me very quickly check that this still works before I give it a proper name. For now, very bad. Okay, now it works. Because what I really would like to show is that we can, of course, have an array of shapes. And one of these shapes could be a square, but another of the shapes could be a triangle. And then let's say there's another triangle, just smaller, and then another square in yet another size. One of the most beautiful aspects of this sort of polymorphism is that we can define lists or arrays where we don't keep track of all the different details of the different types, of the different concrete types that we're putting into it. And this can make it possible to basically define plugins, extensible components of our application, etc. So inheritance is really and polymorphism are really very powerful tools in order to build any sort of advanced dynamic application. Dynamic in the sense that it supports dynamic changes in its behavior. So if we go through all the shapes, and for each shape we draw it well. First of all, look, we only have the name and row here. Why is that? Of course, because we don't know if the shape is just a shape, because it could also be just a shape, or whether or not it's a square or a triangle. So C# is conservative. It only shows us the things that can be used without risking getting a very nasty structural error, like, hey, you're trying to call a method, but this method literally just doesn't exist. Now, of course, if we run this, we see that, okay, we're drawing, the first square, the first triangle, the second square. So, very good. And yeah, you can imagine the flexibility of this. One thing, though, that is not particularly pretty is the definition of the shape. There are two ways of improving this definition. One could be to turn it into an interface. The slight issue of the interface, though, is that, well, first of all, the interface can only model public things. So we have to drop the public modifier, and everything is the equivalent of virtual, or better yet, indeed, abstract. But also, because this name property is just part of the interface, well, it's not an implementation here. And what we get is a complaint that square and also triangle does not implement all the members that are required. So we could say, okay, you know what, just implement it. And for the name, it doesn't matter that much, honestly. Oh, we don't have a base name, of course. This dot name. You see, there's plenty of stuff that I need to do. But you can see that the class shape was actually doing something that was, to an extent, useful when we don't need to override a method from an interface. It's captured automatically. And now we have to do exactly the same in the triangle, because the shape now doesn't contain any part of the implementation. The shape is completely, well, dumped down to only the interfaces. That's not ideal. There is no constructor, so we are sort of left on our own. Again, not a tragedy when it's just about a single field, but also the old draw implementation. Yeah, that's a pity because we've kind of lost it. But anyway. There is a very interesting hybrid between classes and interfaces, which is called abstract classes. So let's say that we actually want to preserve some of this logic, especially the logic surrounding the name of the shape. So we can mark the class as abstract, and by marking the class as abstract, we can say that a method, such as draw, is abstract. Abstract means that we don't provide an implementation, just like for an interface, but because shape still is a class, then I'm still allowed to have the name, to have the constructor, etc. Well, oh, of course, we cannot make the call to the abstract base member because, well, it's simply not there. And let's see. Well, and now C# is happy again. What is it? Oh no, it isn't happy. Wait a second. Oh, sorry, it was just the intelligence. This fancy intelligence being a little bit late. All right, and so thanks to abstract classes, we have the possibility to mix interfaces, and those are the abstract members. We can have abstract properties, abstract methods, etc. But we can also have plenty of fully implemented, you could say, business logic inside the abstract class, so that the classes that inherit the abstract class may specify the things that are abstract, which are therefore missing, but to make use of the things that are provided. I have to say, this is very exciting, but it's also very easy to get wrong. So yeah, I would advise some caution. But we'll look into caution in a moment. Philosophy of inheritance has some limitations. Inheritance only works for hierarchical structures, but it does not work well for interconnected structures where a given entity can be seen within multiple overlapping hierarchies at the same time. For example, suppose that we have person inherited by teacher and student also inheriting person. But as soon as we start encountering edge cases, which aren't even that much of edge cases, such as a part-time student who also teaches somewhere else, because as a teacher, doesn't matter your age, you might also decide to be a student somewhere else, then, well, you lose the ability to represent things. And actually, even if you wanted to, so let's say we had a person, and then we have a student inheriting person. Okay, so far so good. Teacher, clearly also inheriting from person. But let's say that we want to have a student teacher, who is both a student and a teacher, inheriting from student and teacher. This is not possible. A class cannot have multiple base classes, only one. There is only one possibility for inheriting one class from another. So, okay, alternatively, we could say, okay, these are all interfaces. When it comes to interfaces, this is allowed. It's possible to inherit. Oh, well, of course, the program with shapes doesn't work anymore. Now, I don't know why, yeah, as usual, the IntelliSense is screwed up. Let me give it a little push. There we go. Now things work, but we've lost the ability to actually put code inside student teacher and student teacher especially. Maybe person we can live with, but the others, yeah, now we've lost. So we've lost the ability to actually implement stuff, and that's kind of an issue. So yeah, it's a challenge. A better alternative, though, than trying to define our whole entities as a huge hierarchy that tries to be super expressive, it is better to decompose our entities and to keep them simple from their components. So an entity will still be the person in our case, but the fact that you're a student is not something that is part of your identity, and as such you would need to put it in the structure of the hierarchy, but the job is rather something that is had by the entity. So we could say, no, we have a person. No, okay, so the intelligence is alive, very good. We have a person, but then we have an interface job. And the person holds a job, so public, job, get, and as usual, I do prefer to have my setters private. Oh no, what happened? I really don't like full tabs with 4 spaces. Okay, anyway, and then we could say that, or rather than job, you know what? Let's give it a better name. Let's say occupation. Yes, much nicer. Occupation. It's a bit more open-ended, I guess. A little bit more flexible, semantically speaking, okay? And you could say you have an occupation, and, well, being a teacher is an occupation. And being a student is an occupation. And also being, I don't know, a stay-at-home mom is an occupation, if someone would like to do that, or a stay-at-home dad would be a very modern occupation, and so on. So now we have all these possibilities for defining occupations. And so if our business requirements change and we say all of a sudden there's a person who's both a teacher and a student, how do we deal with that? Okay, well, one could say you extend the person and you have the primary and the secondary occupations. There you go. Or you could have the occupations. You have many. Oh, pardon. And you have many occupations. And there you go. And you could also say that there are further activities, and then you can have, so the occupation is what we call a component, and the person is what we call the entity, but we could also have the hobbies, and yeah, you could have, I don't know, that running would be, oh, pardon, a hobby, just one, so running would be a hobby, painting would be a hobby, and so on. And off you go. But you could say that a hobby is, in a sense, an occupation, because if you have a professional runner, then yeah, you still want to be able to put it into the occupation. Now, by combining interfaces and their powerful and open-ended inheritance with entities and components, yeah, then you can get very, very far. And this is one of the things I've seen go wrong the most often, to be honest, when dealing with especially junior and mid-year developers trying to capture big structures in an inheritance hierarchy. I know it seems exciting, but it's better to decompose, because the fact that we can only model a hierarchy, so a tree-like structure and not a network through inheritance, means that we have to fit everything into a series of hierarchies, and so we need to decompose, and this decomposition is great. So instead of having a swimmer, which is also kind of a weird concept, because yeah, a swimmer is still a person, right? And one could say, yeah, then you inherit a swimmer and every other thing from person, etc. But then you get stuck, because indeed you could have a swimmer who is also a trainer, because maybe they don't make enough money by swimming professionally, or whatever, you know. And also the nice thing is that if you're given a if you're given a static inheritance hierarchy, like you have the class swimmer, you know, and that entity changes job, you can't change it because now it's a swimmer. It's an instance of swimmer, and you cannot change the instance of the class at runtime for something. But with a person, yeah, you can change the array of occupation and hobbies. So you also achieve the ability to model a domain where things may change, where things may adjust dynamically. So this entity component framework is really powerful and also, to be honest, quite fun to work with. So I hope you actually managed to put this into practice and enjoy it. Thank you very much for listening. This concludes this information-packed but relatively simple little class. The best of luck with your studies and see you soon. Bye bye.